In this example, we're going to continue practicing to see if a limit exists for a given expression. Over here, if I substitute 1 in the place of x, I will not get a 0 in my denominator, so I'm in fact allowed to substitute straight away. If I substitute 1, I'm going to get 1 plus 3 in my numerator, and I'm going to get 1 plus 1 in my denominator, which is 4 divided by 2, which gives me an answer of 2. In other words, as I approach x is equal to 1, in this particular function, I'm going to reach a height of 2. In this next example, you can see that I cannot just simply substitute x is equal to 1, because that will give me a 0 in my denominator. So I have some work to do before I can try and do the substitution. If I still have to try and see if I can remove my problem, I'm not allowed to substitute, so I still write down the information that I'm going to try and find the limit as x tends to 1. In my numerator, I can do a difference of 2 squares, which gives me x plus 1, x minus 1. And in my denominator, I'm going to find that I have a repeated factor of x minus 1. By cancelling those two x minus 1 factors, and then reassessing whether I can find my limit, I need to say to myself, is there a limit as x tends to 1 for the function of x plus 1? As my problem has been removed, there was a removable discontinuity, and now I can do my substitution, substituting 1 in the place for x and getting an answer of 2. So in this function, there is a limit, even though the continuity did not exist when x was equal to 1. There is a limit, and the limit is 2. Let's assess and see if there's a limit in this next function. If I take a look at this function over here, when x tends towards 1, I cannot substitute it in at the moment, because if I substitute this one into the denominator, I'm going to get a 0 in my denominator. But unlike example B, I cannot factorize my numerator, and so there is nothing that I can remove to get rid of that 0 in my denominator. In other words, in this example, the limit does not exist. In fact, if I take a look, I have a vertical asymptote when x is going to be equal to 1. And that vertical asymptote is easily found by taking a look at the denominator. What are the restrictions on my denominator? The restrictions are when x minus 1 is equal to 0. In other words, when x is equal to 1. In this case, there is a jump discontinuity, and that is a result of there being a vertical asymptote, exactly when x is equal to 1. Let's test our limits one more time. In this function, I once again have got a split function. If I've got a split function and I'm interested in the limit as x tends to 1, then I must take a look at it from the left and from the right. Now be careful to take a look at what you're working with. If I want to find the limit as x tends towards 1 from the left, that is actually the second portion, and so that uses the part of the graph that is represented by 2x minus 5. Substituting a 1 in the place of x, I get 2 times 1 minus 5, which gives me an answer of minus 3. Now going to the portion of the graph as x tends towards 1, but from the right-hand side, in other words, from the x values that are greater than 1, I substitute that into the portion of the graph represented by x minus 4. And now the limit is going to be 1 minus 4. In other words, I reach a height of minus 3. As I reach the same height for both portions of the graph, there is a limit as x tends towards 1 from the left or from the right of minus 3. As I could not include x is equal to 1, there is a discontinuity when x is equal to 1. In other words, I would have had a hole at the value where the point lined up on my graph at x is equal to 1.